Today you're right. Today is Grand Cawthorn. No surprises for you. Maybe we have again to do the chips thing. Is the presentation the same or is
No, it's not. No, I've changed it. Okay.
I think you are making here. It was there because it wasn't making the bubble, so I think yeah, it was there 5 minutes ago. Oh, okay. So it is around. Robin, do you know where it's headed? How you making the yeah, because we had someone then we had in oh, okay. Here in presentation.
Presentations 2023, no, 24 we've got one.
Sorry.
2023. And we've October version.
Please. Take it out.
Yeah, just take that. Okay.
Need to test.
Sorry?
So you need this is to go forward.
What? Yeah, I'm going backward. Yes.
And then you have your little thing. I'm just going to share the screen. Then Robin, one day we come here together and we do yeah, how to set it up with my little notes. Yeah, it's open, but I don't know. I minimized it nicely. Windows. Screen. And we put you in the presentation mode. And here we have already some audience waiting. Just put it down and we just wait a few minutes. Yeah. And I think we are set up. I just take away my things. Okay. So there is space and eventually we'll turn it down a little bit more. I just need this slide like this now, but then when it happens, new, I will turn it. You think we need more chips or you think maybe not?
All right, I'm all right. It's a bit dark.
It's a bit dark.
No, it was just
I just kind of want to see what we do. If we're ready to refer to check if these are lines.
Hello, everybody. We just wait 2 minutes. We are getting ready. Thank you. Hello, everybody. Good afternoon. Welcome to the Geotalks. And today we have a special talk from a special guest, and it's a talk by Grant Cawthorn and Spike McCarthy. And here in the audience, we have Grant talking to us, and among the audience online, I see that there is Spike today. Welcome, everybody. And yesterday I met Grant here in this room to check up our technology, make sure that everything is all right. And he asked me, Linda, how are you going to introduce me? And I said, oh, I don't know, it's so long, your biography, that is going to take quite a bit of time of the Geotalk. And he said, okay, I solved the problem. I am going to introduce myself. So we are happy to have you here, Grant. Thank you for contributing to the Geotalk series. And today is going to talk about the splitting of magnetite layers in the upper zone of the Bushville complex. Thank you. And click here, it should disappear. That.
Sorry, what should disappear?
This little band.
Oh, okay.
That is, we don't want to worry about it.
Good afternoon, everyone. Thank you for coming or for listening in the distance. Thank you, Linda, for the introduction. As Linda said, I'd like to give you a short geological history of myself. Everyone here will have heard of the textbook Layered Igneous Rocks by Wager and Brown, which was written in 1968. So what was I doing? Oh, sorry, I beg your pardon, I'm going the wrong way. Now, the flyleaf for the book says that G.M. Brown was a lecturer in petrology at the University of Oxford. Well, by 1968, that was incorrect. He was professor and head of department at Durham University in the north of England. So where was I in 1968? I was at Durham University as a third-year geology student. So I got a big dose of Skaergaard and Bushveld from Professor Brown. After that, 1969 to 73, where was I then? I was at Edinburgh University as a PhD student. My supervisor was called M.J. O'Hara. He was the champion of ultrabasic liquids, or komatiites. Now, until 1969, basalts came out of the mantle about as quickly as your grocery delivery from the local shops. Totally unchanged. Mike O'Hara claimed that, in fact, basalts were highly fractionated liquids that evolved very, very slowly before they erupted. In 1969, two people from this university, PhD students, Maurice and Richard Villion, identified and announced the existence of ultrabasic liquids, which were called komatiites, because of the type locality down near the Komati River, near Swaziland. So Mike O'Hara's claims were vindicated. Now, in 1973, while I was still at Edinburgh, Professor John McIver, who was a professor here at Wits, visited Edinburgh because he wanted to do some experimental work on komatiites. So I spent a lot of time talking to John McIver about the bushveld and about komatiites and about South Africa. Then in 1975, I was offered a job there at Wits. And on the 16th of October, 1975, almost exactly 48 years ago, I was met at the airport by John McIver and Spike McCarthy.
Tell us about Tom Clifford. Tom Clifford's called in hiring.
Well, if I must, yes. Okay. I applied for the job. In those days, the head of department was totally autocratic. The head of department was Tom Clifford, who was a Yorkshireman. So am I. So I got the job. But anyway, Spike McCarthy was the geochemistry lecturer here at Wits. So John McIver and Spike and I started a number of projects, but then in 1976, I went on a field trip to the bushveld led by Dr. Tom Molyneux. And I'm sure all of the bushveld people around here will know of two incredibly important papers, fundamental papers about the Eastern bushveld, one by von Grunewald in 1973, and the other by Tom Molyneux in 1974, who produced two fantastic pioneering papers. And Tom Molyneux was involved in the magnetitites. And so because of that field trip, it started my interest, and we dedicate this talk to Tom Molyneux, sadly, no longer with us. So I'm sure you all know the bushveld, the thin blue line is where the main magnetite layer of the upper zone occurs. And I'm going to be telling you about, first of all, magnetites, then a quick reference to the outcrop or the mine at Brits, then Vapatskloof, and finally quite a lot of effort on the Swartkel locality. So this is magnetites. Hang on a second, can we remove that bar at the top? What do I need to do? And then people can see the title.
I try my best.
Thank you, David.
Make them back.
Make them. Just click here. So, okay, good.
Thank you. So this is the famous locality in magnetites, where the main magnetite layer outcrops. It is underlain by an orthosite, and it is a truly remarkable locality. If you think about it, the density of an orthosite is 2.7. The density of magnetite is about 5.3. What a huge density contrast that is between these two layers of rocks. And that layer is probably the densest rock at atmospheric pressure above the mantle, above the core boundary. Anyway, when you see something like that, you've got to wonder how on earth it formed. There's one thing that was overlooked for a long time as not being important, but we found it to be very important. In the middle of that 2-meter thick main magnetite layer is a feldspar partic, plagioclase grains lying generally parallel to the layering. And they'll become important in the subsequent talk. Another example. Now, the magneticite layer is mined for its vanadium, and we have a book published back in 1960s called The Mineral Deposits of South Africa. And the person who wrote the section on vanadium, who was the consulting geologist for Anglo-American base metals, produced the section, the chapter, and a throwaway statement. He said, the bottom half of the main magnetite layer contains 0.8% Cr2O3. The upper part contains only 0.3% Cr2O3. Now, if you know anything about geochemistry, trace elements, partitioning, and the Rayleigh law, you will realize that is utterly, totally impossible. You cannot have a layer of liquid that is thin enough, or a partition coefficient that is high enough, or a combination of two, to produce that kind of change in 1 meter. So one of the things we can conclude is that the Rayleigh law doesn't work. So I rushed through into Spike McCarthy's office and I shared this with him. We talked for an hour. 2 days later, we were up at Magnet Heights again, collecting samples, vertical profiles through the main magnetite layer. And then bringing them back, Spike McCarthy, the geochemist, was preparing standards for our analytical work on the XRF. And I was busy separating magnetite from magnetite. Since the magnetite contains about 97% magnetite, and getting pure concentrates was not too difficult. But everything that I refer to now is about the composition of magnetite, not the composition of magnetite.
Why didn't you use the microscope?
This was in 1978. We didn't have a microphone.
Okay.
You can do it much better by down at the levels of detection we wanted by XRF. And these are the first 2 profiles we got in the paper that we published. The CR content in magnetite, height in meters in the main magnetite, height in centimeters in the main magnetite layer, typically about 2 meters thick. And indeed, the chromium content decreased from like 8,000 ppm down to hundreds of ppm within a meter. We also looked at a borehole core from a mine down in the southeast of the bushveld called Buckupsfloat. And again, we got a very similar profile. Note that this is a logarithmic scale. So we're going from 8,000 down to a few hundred in half a meter. One thing that became more important subsequently was the plagioclase bearing intervals, the feldspar partic that I showed you. And the red bar indicates where feldspar is present. So in fact, this layout is actually divided up into 3 massive magnetite sections down here at the bottom, then number 2 and number 3. So there are 3 feldspar particles. And the significance of that only occurred to us much later. These are three of the borehole cores that we got from Vapetskloof, which we photographed. We sampled them before we thought of photographing them. So there were little gaps in the middle where there are these white numbers. They're not important, but you can see that we can have pure magnetite, and then a section with plagioclase back to pure magnetite, and so on in all of these. Anyway, ultimately we had 7 profiles. Here's the one from magnetite. I'll start with one, and one from the mine and bricks. And then we had 5 profiles from Vapetskloof, which were typically about a few hundred meters apart. And you can see that everywhere there are these significant smooth upward decreases, and then usually extremely sharp reversals by a very, very significant concentration in the section. And again, I remind you, it's a log scale. So in 1980, we published a paper in EPSL, variations in Cl content of magnetite from the upper zone of the bushfire complex, evidence for heterogeneity and convection currents in magma chambers. Now, if we go back to 1980, grain settling was, and in fact, to a lot of people, it still is, often referred to as a mechanism to form igneous layering. But in the late 70s and early 80s, a lot of other ideas were being presented, including changes in oxygen fugacity, pressure, magma addition, double diffusive convection, liquid layering, lateral growth. And our model kind of got forgotten about. There are some more recent ideas, including addition of a slurry onto or into the cumulant pile from below or laterally. And we'll talk about all of these models shortly. I went back to reading the literature all about the magnetite layers, and I found a paper by Hammerbeck in he was in the Geological Survey, which was then called, and he referred to the splitting of the main magnetite layer. And the place was a farm called Slotpot, which means Black Hill, fairly obviously because of the huge amount of magnetite on the surface. It's split into 3 layers. Here you can see the bottom split, which is actually pinching out. Very important. We'll talk about that later. But that's the main theme of my presentation. I've forgotten to mention one thing. If ever I use the word I actually mean myself and Spike MacArthur. This is very, very much a collaborative effort. And we bounced ideas around for a long time, but without him, we would never have got to the conclusions. So we have the lower pinch out, we have a split in the middle. We can't quite see the 3rd split. Let's move to another one. Here you can see rather nicely displayed the middle subdivision and the upper subdivision. And in between all of this pale rock is plagioclase and magnetite in varying proportions. So when I found that paper, we went back and we sampled this outcrop in incredible detail. So let's look at a schematic plan of the outcrop. Here we have the main magnetite layer. There was one section about 500 meters from that photograph of the main magnetic layer, and then another profile where it gets here, and then a partial one, and then lots of small sections of the slits in the magnetite. With it excluding that, this is the scale, just a very few meters, and the scale, vertical scale, that is 0.3 of a meter. That's a bottom pinch out, which I showed you a photograph of, and the other one will be the split there between those two sublayers. All right, if we begin with the N profile, the one that is way to the north of that section, we find starts off with a typical value of 8,000, but now we have a massive abrupt decrease, which we had never found before. And then the next two sections, of A and B, we can see they have now thinned down to 60 and 30 centimeters. Very unusual for the main magnetite layer to become so thin. But you can see that trying to correlate these is very difficult. Now let's have a look at where the layer splits. Here we have one that's complete, and then all of the split sections. Now the important things to note is the shaded areas are the pure magnetite, and the blank area in between is the magnetite plagioclase one. Now, what we find that where we go from massive to disseminated rock, from there to there, for example, the compositions show a continual decrease. We'll look at these in more detail. But where the disseminated magnetite clad rock goes to massive, there is an abrupt break and an abrupt increase. We can show this in a bit more detail. Here's magnetite sublayer 2, magnetite sublayer 3, 3, and 4, and in between are the magnetite plagioclase. So we can follow the composition upwards, steadily decreasing from the massive layer into the disseminated layer. The same here, but where we go from the disseminated layer into a massive layer, there is an abrupt increase in the chromium content. So we decided that the plagioclase appears when the chromium content in the magnetite decreases below 1,000 ppm. Actually, to be pedantic, it's not quite right. It's 1,014 ppm there. So I should be saying 1,015 ppm is where the plagioclase appears. But for roundness, let's call it 1,000 ppm as being the defining composition. So plagioclase appears when magnetite composition decreases to below 1,000 ppm. Now you've seen how laterally variable things are, and due to those lateral heterogeneities in the magma, the felspar partings are not long distance timelines. You can't use them for correlation. They are isocompositional lines, and they're discontinuous. Might work over a few meters, but over large distances, you cannot use them for correlation. Here we can see more of the slits, the different parts. Here we've got split 2 and split 3, split 2 and split 3. We've got this magnetite plagioclase intervening wedge. Now, if it weren't for the fact that these are only a couple of meters apart, one would never really think that there was anything but a continuous sequence all the way through that. Whereas in fact, we would infer, because of what we know from over here, that that is a significant break. But even over short distances, some features can and some cannot be correlated. For example, there's a rather distinctive composition over here in the middle of a layer, which you can see on the two profiles quite close together. But there, the two profiles do opposite things. There it decreases upwards, which we now think is kind of the normal procedure. But here we have an increase upwards. And you can see from the thickness of these profiles, 10, 15, 20 centimeters, we've got very, very detailed sampling. And so there can be differences over short distances. We now think that the splitting of the MML might be a lot more common than one previously thought, where people referred to the feldspar parting as being the only one. The problem is there are very, very few good outputs of the main magnetite layer, where you can see the entire section and work on it. Now, I mentioned this profile, which has got a very abrupt increase near the top, an abrupt reversal in composition, but we can also have a very abrupt decrease in composition. So this one we think is due to a major overturn in the magma, which I'll discuss below. Here we think we have erosion, which has caused that geochemical profile. So how do we do that? Let's look at simplified section. We have a vertical profile and the concentration in chromium, which decreases smoothly. And then there is a sudden reversal followed by a smooth decrease. But now, let's suppose that the section from H1 to H2 has been removed by erosion. So this bit up here comes down to here. We actually have a forward jump in composition, not a reverse. So H1 to H2 has been removed by erosion. Do we have evidence for that? Well, that first photograph I showed you up there at the bottom layer, you can see this pinch out as you go along strike. Here we have another outcrop where there are fragments of magnetite in amorphous. The amorphous aspect weathered and orange pinkish color, but we have fragments of magnetite in amorphous. Here's another section from the Wappert profiles we studied the borehole for. And you can see at the bottom, we have nice regular decreases and abrupt increases. And then in the top 30 or 40 centimeters, we have absolute chaos. And no one can't see it in core. We think that those will be fragments of magnetite hosted in magnetite. So here we have chaos due to eroded fragments. Are eroded fragments common in the bushveld? Well, we think they are much more common than people realize. This is the Dwas River locality of the UG1 chromitite in the critical zone. And you can see this fragmentation of chromitite flakes being eroded from the proximity. Here's another example from the main zone bushveld complex, strongly layered 2-peroxide gabbro, a very special locality that Tom Molyneux showed me. They call this the zebra marker for obvious reasons, but you can see how in places it has been totally brecciated and dumped. So erosion may be a lot more common than we think in the bushveld complex. So let's go on to a more theoretical aspect and look at the origin of magnetite layers. Now, there are two fundamental features that have to dominate any model that one may propose. The transition from anorthosite to magnetite is 1 grain thick. So the process has to be absolutely instantaneous. And secondly, it has to happen everywhere, all around the bushveld, over 300 by 300 kilometers. Those two things often get forgotten about when people do try and create models. Okay, let's go back to the first chemical diagram. The chemical gradients prove that the main magnetite layer cannot have formed by crystal sinking or by a slurry. If you had crystal sinking, you might have the same composition of chromium in magnetite in all the grains, and the same with a slurry. These gradients preclude any ideas about sinking or slurries. Another idea that's become popular is magma addition. And let's have a look at a few aspects of that. So here we've got a model, we've got footwall and orthosite, and there was an existing magma, the green color, and the theory is magma was added, this new magma here, in this yucky purple color. Now, the important thing is that for it to make magnetite, it would have to be fairly dense. So the new magma would pond in all of the basins and will be absent over the higher ground. So if the floor was not perfectly horizontal to absolute incredible detail, there would be breaks and thickening in the main magnetite layer, which we do not observe. So we don't believe that there could be addition of a magma. Let's try another one. Let's look at plagioclase compositions. They might be very useful indicators of fractionation and replenishment of primitive magma. So let's look at, here we've got plagioclase composition, here we've got a function of height. Of a detailed study through magnetite layer number 3, which is quite well exposed. As you can see, the difference between the footwall and the hanging wall is less than 2% anorthite. The same across the main magnetite layer. There, there's essentially no difference. And magnetite layer 1, there's almost no difference. And in fact, that one shows that there is differentiation, not reversal. Likewise, that one. Unfortunately, there's a gap in between where we've got no outcrop. Rather unfortunate, because from about 20 meters below the main magnetite layer to down here, there is actually an increase in the AN content of about 5% AN. Now, that is pretty big in terms of all of the reversals that have ever been documented in the bushveld complex. So we're not saying that there are no reversals do occur, but not across layer boundaries. So the addition of a new magma does not initiate magnetite formation, for example. Here is some more work that we did, which I wish we could do a great deal more. Here we've got the main magnetite layer. Down in the south, we have the town of Stockburg. Up here in the north, we've got magnetites. Now, if you look at the composition of plagioclase below and above the magnetite layer, let's start in the north over here. Oh, by the way, those which are circled are from other authors, people like von Grunewald, John Molyneux, and the guy called Ruben Fett. So those are other people's work. But anyway, we've analysed across the magnetite, magnetites, and virtually the same AN. Again, virtually the same AN content, about 10, 15 kilometers further south. At one of the mines, we have a value of AN 54, both above and below. Here, we do actually have a reversal, quite a big one. But there is one thing I want you to notice, is that this is the same magnetite layer, but the AN content has gone from 60 down to what? 54 at least. So there is a 6 AN unit difference above and below the main magnetite layer, even for the same magnetite layer. That is extremely important. It tells us that that magnetite layer formed not because of a particular chemical composition. And if it wasn't due to a chemical composition, it must be due to a physical process. We need more analyses like these, but the outcrop just isn't good enough to be able to do that in much more detail. So if we go back to the magnetites, we can sample the footwall here perfectly, but there's no way you can sample the hanging wall immediately above the main magnetite layer. So we have the problem that we cannot get pairs of analyses on either side of the main magnetite layer. This is what a good outcrop of the main magnetite usually looks like in the eastern bushveld. In the western bushveld and in the northern bushveld, you just see a few bits of magnetite rubble lying around on the surface. So there's no way you can sample this weathered anorthosite and nothing above it in order to test for this pairing or lack of pairing of the plagioclase composition. Now, Lou Ashwell and I did a lot of work on plagioclase compositions. Really? You're forgetting the couple of papers that we published, you don't know. Okay, so oh, sorry. Yes, sorry. Okay. You can't find fresh outcrop in the field, so one has to rely on borehole core to analyze plagioclase above and below the layer. So here we have the AN content in plagioclase below the magnetite layer and AN in plagioclase above the magnetite layer from a borehole. So each one of these is a different magnetite layer going upwards in the stratigraphy. Obviously, these will be from low down with a higher AN content and going upwards in the intrusion. Now, what Lou and I did, having recomputed the thousands of analyses that he and his students collected from the northern limb, is that the level of uncertainty in a plagioclase analysis is about 2 AN units. So if we had a perfect one-to-one match, in other words, no change in composition, we'd have this line here, 1-to-1. Anything within 2 AN units of that, we would have to say we cannot resolve that as to whether there is magma addition or not. If we had a sample plotted above that dashed line, one might say then there was a reversal and hence magma addition. But you can see from all of those points that in fact there's no real evidence for magma addition. Well, if the extreme gradients in chromium prove that magnetite grains did not sink, what else was there? Well, they had to have grown on the bottom of the chamber by heterogeneous nucleation. So here we'll come to our theoretical modeling. But how do I get rid of this thing at the top? I bet no, that's not
Yep.
today.
Yeah. First checking here. So he went away.
You came back.
And then he came back.
Yeah,
Good.
okay.
Now
Thank you. All right. Okay, so now we need to consider convection in the magma chamber. Convection is normally conceptualized as being due to a heat difference, like this model here, red would be hot and blue would be cold. But that's incorrect. The driving force for convection is actually density. Heat changes the density, and that is why liquids convect. There's density that is important. So when we come to crystallizing magnetite, it lowers the density of the remaining liquid, in this case on the bottom in our model. And so it is the magnetite crystallization that is the driving force for convection. Click on the green.
Just on the slide.
now we should
Yeah. So in the case of magnetites, it is crystallization in the reduced compositional heterogeneity. And if that exceeds the rate at which stirring can homogenize it, then we will end up with heterogeneity in here. Which you can see from this color scheme, which is, in our view, a density model, not a temperature model. And because that is so inhomogeneous, you cannot apply the Rayleigh law. Oh, sorry about this one. So how does convection affect the composition of magnetism? So here we've got what we call qualitative height. Here it is in the liquid, and here it is in the magnetite that's forming from that liquid. So here we're talking about tens of meters only, and here we're talking about tens of centimeters. So let's begin at the beginning. We have, to begin with, we have a temperature. Here is qualitative chromium, iron, and density in the liquid. And here we have qualitative chromium in the magnetite. So we begin at time 1. We have the composition of chromium in the liquid like that. As crystallization begins, the magnetite extracts chromium, decreases, and the liquid at the bottom becomes depleted in chromium, and so we have a profile for chromium in the liquid that looks like that. And then within that we have eddy diffusion and small scale convection. So that's the first gradual decrease in chromium content in the magnetite. Now we have a convection cell that comes down. It brings liquid from there, which is fairly high in chromium, down to there, which is depleted in chromium. So we get a reversal in the chromium content in the magnetite. Gradually, that rather abrupt variation in chromium content gets smoothed out, it gets depleted by a small scale convection. And so we then have first of all, a gentle increase. So that's how we can get depletion, increases, and depletion in the magnetite layer. If the convection cell reaches the floor or the contact here, the change in composition would be abrupt. If the convection cell is sort of in the middle of the, or not in the middle, but above the floor, then we'll get a slow reverse in the chromium, and a slow increase in the chromium content. Now let's go to this one here in a bit more detail. Here we can see that we start off with magnetite 1 forming. It's not layer 1, but first bit of magnetite to form, and it has this composition. Then we have a compositional convection that brings fertile magma down right to the floor. So instantaneously, we get an increase from there to there, and the composition of the second bit of magma is from there to there. Then there's a little bit of interstitial liquid at the boundary, and so we get a little bit of diffusion across it, and we end up with a profile after infiltration metasomatism that shows a slight increase. So the extent of that metasomatism we can quantify. Let's go to back to magnetites, to magnetite layer number 1. The anorthosite below and anorthosite above. One of the very few examples where you could sample plagioclase above and below. But anyway. Now, we took 10 profiles at intervals of 10 meters all the way along here and analyzed every centimeter. And what you can see in all of them is that at the bottom, there is an upward increase in the chromium content. So we would argue that the original profile would have looked like that, going up to over 1,000 ppm. And this bottom sample, or maybe the bottom 2 samples, have been affected by infiltration metasomatism from the liquid beneath. So that will be our view of the scale of metasomatism in the bushveld. Trivial. So let's look at a summary of the observations that we have. The boundary between the anorthosite and the magnetite is very sharp. No change in plagioclase composition occurs across magnetite layers. Extreme vertical variations of chromium exist in the magnetite. Lateral variations of chromium and magnetite exist along strike. There can be a variable number of vertical reversals in chromium in magnetite that exist upwards, and a different number of them in different profiles. Rare major abrupt decreases in chromium also exist upward. Plagioclase gradually appears when the chromium content in magnetite decreases below 1,000 ppm. But the disappearance of plagioclase upward to pure magnetite is always sharp, and CR in magnetite increases above that boundary. So those are the observations which we have to explain. So the interpretation is that there was no addition of new magma. Magnetite grains could not have sunk, but grew on the bottom. The basal magma decreased in density as magnetite formed, causing convection, which resulted in intermittent but abrupt increases in chromium in the magnetite. Convection could be vigorous enough to cause erosion of the floor magnetite that had just previously formed. Magnetite only and magnetite plus plagioclase formed simultaneously along the floor because of lateral inhomogeneity in the magma. So the event had to be chamber wide, 300 by 300 kilometers, and instantaneous, not even 1 grain thick. There is only one model that we can think of that could produce such an instantaneous event, and that is earthquake-induced shock nucleation. We believe that's the best possible explanation to explain all the features that we see in the magnetite layers. And the important conclusion was the one where I would like to get more data, showing that the composition of plagioclase changes laterally at the main magnetite layer. So the crystallization of magnetite was not related to chemical composition. It had to be a physical process. So a couple of months ago, after 40 years of thinking about it, Spike and I finally published our paper in the Journal of Petrology on the geochemical anatomy of the main magnetite layer in the Bushveld complex, South Africa. I thank you.
Thank you so much, Grant and Spike. Is there any question?
Yeah.
Let's start maybe with Scott.
Scott, yeah.
Just a quick question. I think maybe I misunderstood something, but it seemed like towards the beginning of the talk was maybe presenting that some of these feldspar zones were not time related, right?
They're not. They're not.
But then towards the end of the talk, you're saying that this is that the magnetites represent a time relative event.
Yeah. The magnetite layer is a single time event,
Okay.
but within it, when you get around to magnetite plagioclase forming, it can occur different places, different heights within the different profiles of the magnetite.
Okay. Okay.
Did we have a question?
Yeah, so firstly, great talk, thank you. Your model that you put up of density driving convection. If this is a mechanical process that's shock induced, it seems like the model started off with a pretty much homogeneous density, and it looked like the density was then decreasing primarily at the base of the model.
Yeah, exactly.
Is that related to this chemical shock process?
Yeah, well, a physical shock that initiates nucleation.
Yeah.
Like tapping the side of a beer bottle.
Do we expect
You
to
get a
have
sudden
that
burst of nucleation if you have a shock wave.
only at the base?
At the back, yeah. That is, I mean, take a glass where you can see it, you know, of aerated liquid. Where do all the bubbles fall? On the sides, and then they bubble upwards very quickly. So the nucleation is easiest on a pre-existing physical boundary. That's why we call it heterogeneous nucleation. If a crystal grows in the middle of a magma chamber, we'd have to call it homogeneous.
Does that explain the volume of magnetite?
There's no way one could work out what the effect will be in terms of volumes. But I mean, the amount of magnetite in terms of the whole Bushveld complex is not all that great. It's actually, Tom Molyneux and I published a paper all about this, and the total amount of magnetite in the upper zone is about between 8 and 10%. The upper zone is the biggest of all of the zones and most extensive. But even so, in the whole bushveld complex, in the whole magma chamber, or the Rustenburg layered series, as some people want to call it, is probably no more than 3-4-5% magnetite.
And just a follow-up question, if there's no others, how does that correlate with the chrome variation across magnetite?
Each magnetite layer we have studied always shows a decrease in chromium upwards, because you're taking a lot of chromium out of a very, very thin section of the liquid at the bottom of the chamber.
Please, Sue.
One thing that is, I've always thought is very important in these rocks is the observation, and I swear I saw it in those drill cores that you showed. And that is that in the feldspar bearing stuff, you can clearly see places where the amount of feldspar really decreases from a lot to a very little of constitution. You didn't really mention anything about this in your story.
Okay, that's because the composition of the liquid is not homogeneous. It's strongly zoned. And in fact, this is one area where Willem and Race and I would agree, is that the crystallization of plagioclase slowly occurs at the bottom because as the liquid reaches that 1000 ppm chromium content, but that's not the liquid content, but in the magnetite. As the liquid gradually reaches that, it begins to crystallize plagioclase. And as more and more of that liquid is in the less than 1000 ppm chrome compositional field, we get more and more plagioclase. But your observation is absolutely correct, sir.
It looks very much like sediment.
It does, but you've got chromium in the magnetite that varies.
Would that be driven by the magnetite forming at different levels in the chamber?
No, the magnetite forms at the bottom.
Please.
So the question I have about the earthquake shock induced crystallization is, where do you think that's occurring? Because the energy dissipates as it expands, and so it is not going to be the same amount of energy coming and so you know, if it's subcritical over here and this little earthquake triggers it, how, how much energy do you actually need to trigger this? And how are you taking into account participation of that energy over the 3 to 400 kilometers?
Just repeat this because maybe Sue is in the voices. It's just that, yeah, the amount of energy required for earthquake and how it can this energy dissipate through such a large area like the Bushwick complex.
Yeah, it's a very valid question. How big the earthquake is? Okay, let me backtrack. If you put 8 kilometers of magma into the high level crust of the earth, you are going to cause earthquakes and instability. I think you and I wrote a paper about this at one stage. Yeah. How I don't know the physics of how that would extend.
What sort of pressure change?
Yeah. So I guess the main question is what how much energy is needed, because I don't know to initiate the crystallization. And if more than that energy comes through or less, or how much is needed to do that?
I've no way that I could do any calculation like that. What we know is that when volcanoes erupt, they're associated with earthquakes, and there's a lot of evidence that nucleation does occur during that process. Extending it to 300 kilometers, I accept that is a good question. Willem,
Excellent. I really enjoyed that a lot. I just want to know, and I'm sure that you know, that we have these really strong and significant chromium reversals at the base of magnetite layers. Which to me would suggest that maybe a process just cannot be as simple as just a change in pressure. I don't know if you have any thoughts about that, chromium reversals.
Question about the chromium reversal.
well, I showed you how an upward chromium reversal could occur by infiltration metasomatism. So it depends on the composition of the magma that's been depleted and made the underneath section, and the fertile magma coming down with a higher chromium content. But then you can either have mixing of that upward rising residual liquid, or later infiltration, changing the composition of the magnetite.
Can you expand on that? So look at
Yeah.
Yes, please. Yeah.
Okay, if we look at magnetite layer 1 specifically, it has this chromium reversal, which you and Spike recorded.
Yeah.
I mean, underneath that, okay, so I would suggest that that could not be convective overturn, since the magnetite layer 1, I mean, it also spans for hundreds of kilometers, like the main magnetite layer. The magnetite directly underneath magnetite layer 1 is extremely poor in chromium. So I don't see that we can have the existence of a chromium-rich liquid there. And I mean, something else that's really interesting to me, at least, is that xenolith you in that magnetite's locality, where if you look at the magnetite on top of the xenolith and adjacent to it, and you compare all your analyses, you see there's not a significant increase or decrease. What you see, the ones that are adjacent to the xenolith, if you plot that data, they kind of they bracket the values you see on top of the xenolith, which would suggest to me it's not all of that, would suggest it's not convective overturn, it's not a liquid coming from below.
Okay. Number one, you talk about the magnetite layer number 1, and then you talk about composition underneath magnetite layer number 1.
Yes.
What have you analyzed there? Have you analyzed the whole rock?
No, pure magnetite separates,
You've done magnetite, and they are lower,
extremely low.
extremely low, yeah, because they are the end of fractionation of one cycle, and the liquid has got totally depleted. Then a convection cell comes down, bringing fertile magma, which then starts making a magnetite layer. But there's interstitial liquid in the anorthosite and the footwall, and that interstitial liquid is percolating upwards and changing the composition of that very basal section of the magnetite layer. Okay, the second one is a long, complicated answer. If you read our JPEG paper, you will find we have a long, complicated answer as to why those are xenoliths and not floor fragments. So I'm afraid I haven't got the diagrams in my talk that cover that. I excluded that because of a time factor, but it's in the paper I mentioned. Sorry, I can't show you the diagrams which we had.
Just take a couple of questions, maybe Willem, since you are both of you very expert in this, I think you should have a conversation.
Yeah,
I just had here from the audience that said, can it be the Freda for impact that day?
No.
And the Roger is here, and he says no. Because it's younger than the bushveld.
What I would say, and the last time I spoke to Spike, i.e. this morning, he would agree with me. Yes, it's not the Vredebot impact, but it's another one.
Okay,
Yeah, that is in the middle of the bushveld.
Roger, please go ahead.
So just a quick one. On news.
You want to come here?
The issue of the metasomatism reversing compositions. Has anyone tried to see whether there's zoning in the magnetite grains in that interval, where you've got the low chromium pulls, and then they're obviously using in the enrichment.
Okay, there are two issues here. One is that all of the grains have annealed into absolutely massive grains. They've totally annealed, and so the chromium gradients have been totally obliterated. Well, I say they're totally obliterated. We actually published a paper in 1981 where we showed that a single grain of magnetite, which was 2 centimeters in size, actually had a vertical chemical gradient decreasing in chromium. But there's been so much recrystallization, we can't recognize primary grains.
Okay, here another question from the
Sorry,
audience.
yeah.
The MML appears in different layers. What can you say about the shock model?
So I don't understand about it appearing in different layers. The MML is a layer 2 meters thick, which has these feldspathically partings which are laterally discontinuous within it. So the shock model can occur frequently. In volcanic zones, we can get earthquakes very frequently during a volcanic eruption. So repetition of earthquakes and the subsequent shock is perfectly possible.
Yeah. I thank everybody. This is a very interesting conversation. You will receive a lot of questions, I'm pretty sure. Thank you, Grant Cawthorn. Thank you, Spike, for your contribution. And thank you, everybody, and see you next week. Thank you. So there is an email address here from a person called Fabian Friedrich.
Yeah.
Would you like to?
Could you reply and say you can have my email? Yeah.
I'm going to take a picture. Setting.
Oh, he's in one of the exploration companies.
Yeah.
In the northern. Did you?
I took a picture.
Yeah.
Send you touch by the email address.
Mm.
Bye, Grant. Bye, everybody.
Thank you, Grant. That was great. Enjoyed it. Ciao, Linda.